Induction and deduction. These are forms of argumentation where the conclusions are formed in two different ways. Induction is a weaker form where those conclusions based on induction are invalidated or refuted as soon as someone comes up with a counterexample. Deduction is much stronger. Conclusions that are formed based on a deductive argument cannot be refuted by counterexamples. Induction are conclusions that are based on observations. These conclusions are called conjecture. A formal definition is a method of reasoning in which general laws are inferred from a number of particular observations. So if you see something that happens all the time and you come up with this conclusion, that conclusion is called a conjecture, and the way you form that conjecture is through induction. We will use inductive reasoning with this example of sets to form conjectures that will be used to identify which objects are in the intersection. Because we will be using inductive reasoning, the conjectures that are formed will be based on our observations. Let's observe the first set of objects. The left set contains a small green parallelogram, the right set contains a large red pentagon, and the intersection contains a small red triangle. Based on the observations, a valid conjecture may be the intersection contains small red triangles. Let's look at a few more objects to see if this is true. With this second set of objects, we can observe now that the left side has an added small blue diamond, the right side has an added large red circle, and the intersection has an added small red rectangle. The addition of the small red rectangle in the intersection is a counterexample to our previous conjecture. Based on our current observations, it is no longer true that the intersection contains small red triangles. Our new conjecture may be the intersection contains small red objects with 3 or more sides, or we stated the intersection contains small red polygon. Let's look at a few more objects in these sets, confirm that conjecture. With these objects, we observe now that the left set has an added orange rectangle, the right set has an added large red hexagon, and the intersection has an added small red circle. The addition of the small red circle in the intersection serves as a counterexample to our previous conjecture again. Based on our present observations, it is no longer true that the intersection contains small red polygon. So our new conjecture may be the intersection contains small red objects. As more and more objects are added to the sets, you'll find more counterexamples you can use to come up with better and more exact conjectures about which objects belong in the intersection, or you may simply find that the current conjecture that the intersection contains all small red objects is true. This is an example of how inductive reasoning is used. Deduction. These conclusions, which are called theorems, they follow logically from a set of premises. So logic is applied to these initial statements, and then we end up with these conclusions. There are no counterexamples for deductive argument. An example is this classic and basic deductive argument: all men are mortal, Socrates is a man, therefore Socrates is mortal. This argument, these first two statements are the premises. These are general statements. All men are mortal, Socrates is a man, and our conclusion based on these two statements is our theorem. That theorem here is Socrates is mortal. This is a form of deductive argumentation. Looking at patterns, we use induction to try to find the pattern that's generating each of these terms, and each of these numbers are considered terms. We try to find out what's generating these terms, and then apply that to find out the very next term or the very next set of terms. When looking for these patterns, there's a few things to pay attention to. One thing is, are these terms increasing as we go from term to term? So if we start here at 3, our next term is 20, so we do see an increase in values in our terms. Our next one is 37, next one is 54. So these are all increasing terms. When our terms increase, we have two operations that cause that increase, either multiplication or addition. If the terms are increasing slowly, we're going to think about addition. If there's a fast increase in our terms, that's most likely going to be multiplication. So to get from 3 to 20, the first thing, if I try to multiply 3 by some number, the closest I can get to 20 is multiplying that by 7. 3 times 7 is 21. That's too large. 3 times 6 is 18. That's too small. So I can't multiply 3 by some value to get to 20. So multiplication is out of the question. If I start with 3 and I add 17, then I do end up with 20. That is the next term. I'm guessing right now, my conjecture is add 17 to the terms to get to the next term. The second term is 20. If I add 17 to it, do I get to the third term? 20 plus 17 is 37. That is my third term. And lastly, I'm going to check 37 plus 17 is 54. My conjecture is that to get from term to term, I have to add 17 to the previous term. So my next term would be 54 plus 17. That would be 71. In this pattern, we see also an increase in terms. But notice we start off at 2 in the very first term, and by the fourth term, we're already at 686. This is a very fast increase in our values. This usually implies that multiplication is being used. So to find out what's causing this growth in terms, we start with the first term. What's going to move us from 2 to 14? 2 times which value is equal to 14? Well, 2 times 7 is 14. So my conjecture is that if I multiply each term by 7, I will get to the next term. So let's apply that. Let's see if that's true. 14 times 7 is 98. And if I take 98 and I multiply it by 7, that is 686. So the very next term is going to be 686 times 7. The other thing to notice in our pattern, so those were both increasing patterns, were term by term we saw an increase, one faster than the other. We'll also notice a decreasing pattern. So 29 to 26, that is a decrease in patterns. There's only 2 operations that will decrease or cause the decrease in terms. That is either division or subtraction. Now, just like multiplication and addition, these decrease at different rates also. If we're subtracting, we see a slower rate of decrease. If we're dividing, there's a faster rate of decrease. So these things get small. With division, the terms get smaller a lot faster. With this series of numbers, we do see that decrease. So it's either going to be one of these 2 operations, either subtraction or it's going to be division that we have to use to move from one term to the next. If I try to divide 29 by anything, by any integer value, I am not going to be able to get that equal to 26. There is no integer I can use to divide 29 in order to get to 26. So I'm also noticing at the same time is this decrease is kind of slow. I start off at 29, then I'm at 26, then 23, and then 20. So within 4 terms, I'm still within the 20s. I know division doesn't work, so I'm going to try a subtraction. 29 minus which value will give me 26? 29 minus 3 gives me 26. So my conjecture is if I subtract 3 from the term, I will get to the next term. Let's see if that's true. 26 is the next term. 26 minus 3 is equal to 23, and that is the very next term after 26. 23 minus 3 is 20. That is the term after 23. So that means that my conjecture is holding up. It's probably true. And the next term is going to be 20 minus 3, which is 17. Now here's a decrease in terms. Looking at 128 down to 64, we do see that decrease. So we should be thinking of only 2 operations. Those are subtraction or division. If we start with subtraction, 128 minus which number is 64? Well, that would be 128 minus 64 is 64. And apply it to see if that's what's giving us this pattern. We would apply 64 minus 64 is equal to 0. But our term after 64 is not 0, it's equal to 32. So subtraction is not being used to generate this pattern. So let's try division. 128 divided by which number is equal to 64? Well, if I divide 128 by 2, I get 64. So my new conjecture is if I divide the terms by 2, I will get to the next number. 64 divided by 2 is 32. That is what the third term is, or the term after 64 is 32. If I take 32 and I divide that by 2, I end up with 16, and that is the term after 32. So far, my conjecture holds up, that to find the very next term, we take the previous term and divide that by 2. You should also be aware of alternating values showing up in your patterns. If you see something like this where you have a positive number, the next term is a negative number, the term after that is positive, or the term after that is negative. When you see this alternating values, positive, negative, then one of two operations are being used. It's either going to be multiplication or division. And it's going to be multiplication by some negative number or division by some negative number. That's what's going to cause the alternating signs for our terms. So to find out which one is being used, look at the absolute value for the terms. The absolute value for 1 is 1. Absolute value for negative 3 is 3. The absolute value for 9 is 9, and the absolute value for negative 27 is 27. Since the absolute value of the terms is increasing, then we know multiplication is being used. We know two things so far that's generating our series of numbers. First is multiplication is being used, and the second is we're multiplying by some negative number. Now, which number times 1 will give us negative 3? Well, that would be negative 3. So my conjecture is that in order to get from term to term, you would multiply the previous term by negative 3. So 1 times negative 3 gives us negative 3. Negative 3 times negative 3 gives us 9. 9 times negative 3 is negative 27. So my conjecture holds so far. If I take the previous term and multiply it by negative 3, I end up with the next term. So the term after this would be negative 27 times negative 3, and that would be equal to positive 81. Now this pattern shows, again, the alternating signs. We have a negative number, positive number, negative number. However, it's different from our previous example in that the absolute values for each of these terms is not increasing. Instead, the absolute value for the terms is decreasing. So because of the alternating values, we only have one of two operations that can do that, multiplication or division. But because of the decrease in absolute values for each of these terms, it has to be the division that's being used. Because of that, we have these two facts. We know that division is being used, and it's going to be division by a negative number. Now, looking at the first term, negative 64, and knowing this fact, negative 64 divided by what negative number is equal to positive 16? Well, that would be negative 64 divided by negative 4 gives us positive 16. My conjecture is to get from term to term, you would divide the previous term by negative 4. Let's test this. 16 divided by negative 4 is negative 4. My conjecture is holding up so far, which means my next term might be negative 4 divided by negative 4, which is equal to 1. Incidentally, we end up at 1 here. If we wanted to find the next term after this, watch what happens. We have 1 divided by negative 4. So our term would be written as a fraction, negative 1/4. And the term after that would be negative 1/4 divided by 4, a negative 4. And recall, since we don't divide fractions, we end up multiplying by the reciprocal of the second fraction. We would end up with negative 1/4 times negative 1/4, and that would be equal to positive 1/16. So the series, after all that's said and done, your series would look like negative 64. If our conjecture is true that we divide each of the terms by negative 4 to get to the next term, then our series starts off here. We end up at positive 1, negative 1/4, and positive 1/16, and so on and so on. Looking at a problem like this, what they're asking you to do is identify the meaning of this symbol. What does that pound sign mean? So if we have a base A raised to the power 5 with that pound sign, and then the same base A raised to the power 4, what do we do with those exponents, 5 and 4, in order to end up with this base A? So the base stays the same, but the exponent ends up at 13. In our second example, same bases, all the bases are A, the second power, and our second base is A to the 6th. How do we get these exponents, 2 and 6, to end up at 12? And likewise, how does 6 and 3 end up at 13? When we answer that, we know what this hashtag or pound sign symbol is telling us. Most efficient way to do this is just test each of these expressions over here with the exponent. So here in our first example, x is 5, y is 4. And is this true? Is 2x plus y equal to this value of 13? So let's see. We're going to do 2 times our x, which is 5, plus the y, which is 4. This gives us 10 plus 4, which is 14. This is not equal to our 13, so we can count this one out. That's not what our rule is, or that's not what's described by the pattern. Likewise, we check the second one. Again, x is 5 and y is 4. We're using this first example still. X is 5 plus 2 times 4 is 5 plus 8, which is 13. That is equal to this exponent. So we're going to test it with this set, the second set of exponents in our example. In our second set, the x is equal to 2 because that's the first exponent. Y is equal to 6, that's our second exponent. And so we're looking at 2 plus 2 times 6 is equal to 2 plus 12. This is equal to 14. That's not the value we have here. We have 12 here, so this one fails at the second example. Let's move on to our third example, and we're going to start again with this very first example that's given to us. There, x is 5 and y is 4, so it should be 5 plus 4, and then plus 4 is equal to 9 plus 4, which is 13. That is what this first exponent is. Looking at the second example, where x is 2 and y is 6, we would end up with 2 plus 6 plus 4 is equal to 12, and that is the value for this exponent. So now we're going to try our very last example that's given to us, where x is equal to 6 and y is equal to 3. These are the values for the exponents here. So with this pattern again, we're going to have 6 plus 3 plus 4. 6 plus 3 is 9, plus 4 is 13, and this exponent agrees, which means that the rule for the hashtag, or the pound sign, says if we have the same bases and the pound sign is our operator, that is equal to the sum of the exponents, x plus y, plus 4.